Maria Esther, if I can ask a question.
Yes.
Perfect. Yeah. So actually, the question was exactly this: if you can hear me. So you can hear me and see me well,
Yes,
right?
I can hear you and see you.
Perfect. Okay. Thank you.
If
That's
you have
all.
a presentation, you would like to try to share a slide, your slides.
I'm gonna be the chair in this session,
Yes,
so I think
you
for
will be
the
the chair.
rest, yeah, we will see. Perfect. But thank you.
You're welcome.
Just to say hello to all our speakers. I think we're all here, so that's good. We can go with the order that there was in the program. If you have any issue, any technical issue, let me know, and Maria Esther, so we can. Yeah.
Let's wait a bit, 3 minutes till 2 p.m. Okay, thank you. The session will be recorded as the whole conference, so thank you for this.
Hello, Georgios. Vangelis told me to send these greetings, so he especially asked me to send these greetings.
Thank you. Say hello also from me. It's been a long time since we saw each other.
Chiusa il done my part.
Okay, I still see people coming in, but maybe we can start, and I guess more people will join in a bit more. Yeah, I see more people coming. Hello, Connor. Welcome everyone to session 8 about innovation, technology, and competitiveness. My name is George Saxakis, and I'm a senior researcher at Holistic. It's a consultancy from Greece working on climate and energy modeling applications. But here in this session, I represent the Paris Reinforce project, one of the co-organizers of the conference. The Paris Reinforce project is Horizon 2020 project about designing science-based and stakeholder-informed climate policies. It's coming towards its end, so one of the presentation here from Sigit is gonna talk more about the results of the project. Few words about the session. The session is about innovation, as said, and specifically we'll look at the role of expert knowledge, game-changing innovations and technologies, and spillovers in knowledge creation, as well as digitalization and societal change for large-scale decarbonization. In total, we'll have 4 presentations and some housekeeping rules. So we have 1.5 hour, and so we'll have for each presenter around 15 minutes presentation, with 5 minutes for each questions afterwards. And then with the remaining time, we can have a general Q&A and concluding remarks at the end of the session. Try to keep the time as much as possible because of the virtual environment. It's not possible to extend it because I think after a while it's gonna just shut down. And if anyone has any technical issue, either from the speakers or from the audience, let me know, and as well Mariaster Casinelli, that she's here from the part of the organizers. Finally, for all your questions to the presenters, please write them in the chat box in the interface. So without further ado, let's start with the first presentation from Sigit Perdana. Sigit is a scientist at the Laboratory of Environmental and Urban Economics at PFL in Switzerland. And he's going to present a study about what do experts perceive as critical game-changing innovations to consider remodeling and policy. So Sigit, the floor is yours.
Thank you. Okay, I would like to share the screen. Okay, hopefully you could see something.
Yeah, we can see that.
Okay, cool. All right, so I hope you can hear my voice clearly. All right, thank you very much. Good afternoon, everybody. Thank you for joining in the sessions. Today, I'm going to talk about the game-changing innovations and then how the climate and energy expert perceive about these innovations in the context of deep decarbonizations. Well, actually, as George have already mentioned, this research is a part of H2020 Paris Reinforcement projects, the projects where I myself and also George and some of the participants in this conferences are involved. I'm going to start by pointing out why the study is important, why we do these kind of things. First, because game-changing innovations, their roles in deep decarbonizations are not fully understood. For example, as a modeler, I have to confess that sometimes we overuse CCS, carbon capture storage in modeling to reach the mitigations target, and neglecting the constraints that these innovations might face, right? So by evaluating game-changing innovations from the expert perspective, we are able to support the design for more realistic decarbonization scenarios and to improve net policy studies. Okay, and this is the outlines of my presentations today. So I'm going to start by the definitions. What do we mean by game-changing innovation? So basically, game-changing innovations, in a simple way, it is low-carbon innovations. So it could be something related to mitigations technology. We call it core technological innovation, or something related to less technological innovation, which is much more correlated to behavioral changes. We call it other disruptive innovation, right? Let's start from the technology first. There are a lot of mitigations technologies, but we will not evaluate all. Instead, we are focusing on the innovations or technology that are still in the basic research level or small scale development. So widespread and commercially available technologies such as wind power, hydro is not going to be evaluated because it has been commercially available. And for this purpose, we refer to the study of KNAP in 2017, who classified technology based on their technology readiness level. And then we further categorize them into four. So technology relating to transportation, industrial sectors, building and construction, and CO2 removal. And then for another innovations, we call it other disruptive innovations. This is less technological and much more correlated to behavioral changes. And for this purpose, we refer to the study of Wilson. I hope you could see my cursor here. Again, we divide them into four categories. The first one is innovation related to mobility, related to food and consumption, building and interconnectivities, and the last one, energy supply and distributions. So let's check the first one, core technological innovation in transportations. For this, we have first aviation's biofuel. So the blue alphabet here just represents the acronyms that we use in our analysis. So just bear in your mind. And then the second ones, we have hydrogen's aircraft, and also we have hyperloops. For for industrial sectors, first we have advanced biofuels. So it refers to the second generations of biofuel productions using cellulosic material such as algae, as you can see in the pictures right here. And then we also have carbon capture storage, or CCS, everybody know it. And then the last one is related to the iron and steel production. So we have two technology here. First is related to the electrolysis. We call it iron ore electrolysis. And then the second one is using hydrogens in this electrolysis process. We call it hydrogen in steel making. We also have technology in building and constructions. We have alternative building material for steel and cements, much more on the concrete. And then the last one is the technology relating to the CO2 removal and other technology. So we have bio-CCS here, everybody know it, and biochar. Biochar is actually a charcoal that is produced by pyrolysis, which is very important for carbon sequestration. We also have the direct air capture, or DAC, so capture CO2 directly from the atmosphere. We also have ocean liming. So ocean liming is the types of technology that could improve ocean alkalinity, that we could absorb heat and then catch the atmosphere, CO2 from the atmosphere. We also have nuclear fusion. Don't get wrong with fusions because nuclear fusion is different thing. So basically, we produce a massive amount of energy from hydrogens with a small radiations, and then next generation energy storage, which refer to high performance energy batteries. Okay, that's for technology. Now we move to other disruptive innovations, less technological, much related to behavioral changes. First, we have something related to mobility. We have first alternative form of automobility, such as car sharing, as you can see from the icon here. And then alternative of automobility, so it refers to the vehicle itself, like e-bikes, or reduced demand for mobility. So it could be activity like home working, teleconference, like we are doing now. We also have something related to food. So it's diet. So we reduce meat, very, very clear. Or growing our own food. We call it urban food production. Or cutting the distribution line. So customers will buy food directly from the producers. So we call it producer-customer relationship, and reduce demand for food. And for buildings, Well, actually, the target is to create net zero home. So it could be supported by activities such as interconnectivity for optimized usage using smart appliances, or optimizations of thermal, or reduce space because smaller space consume less energy for sure. And then the last one is related to the energy supply and distribution. So we are moving from net zero home to net zero city, right? So it's identified by energy supply distributions with new service providers that provide alternative energy of green energy, let's say, integrating customers into grids, which is, yeah, all of the electric vehicles could be recharged timely and decentralized energy supply with solar PV, with the storage or microgrids and turbines. All right. So all of these game-changing innovations in climate change were evaluated uh, with our expert survey through an online survey. So we have three questions that we were asked to our expert respondent. The first one is about their mitigations potential, whether it's going to be very low to very high, and then the expected times that these innovations will be commercially available or start being implemented, and then the risk of these innovations to be delayed or never been adopted. So if it is insignificant, more likely it's going to be delayed. If it is critical, sorry, if it is insignificant, which means that it's going to be on time, the implementations, and if it is critical, more likely it's going to be delayed. The respondents also have the options of not able to respond, and then we have a targeted respondent because we aim for the expert survey. So we got some from our stakeholders in our project, and then the recommendations of our consortium partners. So at the end, we have 260 responses from 56 countries, and this is our respondents profile. We have somebody from academic. We also have private sector, national government, those who work in international institutions, and NGO. And 40% of our respondents are coming from Europe 27, and another 60% is from the rest, right? Now we try to take a look at on the survey result, the survey answers, and then do like a general statistical analysis. We would like to see the general distributions of their answer. We start from the mitigation potential, the first questions that we were asked, okay? So for this purpose, we first translate the survey answer from linguistic to numerical, and then takes the mean value, and then we do it for each of the innovations, and then we got this graph. So the green one here is represent the technology, and then the white one here represent the non-technological innovation. So one thing for sure that for according to the expert, next generation energy storage, hydrogen in steel making, alternative building materials, and iron ore electrolysis. They are perceived as the innovations with high potential of mitigation, but not so for the AC, hyperloop, ocean lining, and even nuclear fusions here. So the perception is quite diverse for technology. However, if we take a look at on the other disruptive behavior, the white bar here, it is a little bit more uniform. So most respondents perceive this as moderate to high potential in mitigations, except for food. Okay. Now we next see the expected times that it's going to be commercially available. Most of the respondents think that like nuclear fusion, ocean lining, hyperloops, and even the AC here, they're going to be available post 2050 with a relatively higher share of this respondent perceive this may even fail to launch to begin with. Okay, but we have a different picture for the ODI. For less technological innovations, all can be adopted within the next 2 decades, 2034 here, except a little bit challenging for urban food here and relating to food and consumptions. Next, we are mapping the results, mitigations potential, and then the risk of transition. So if we take a look at this, the thing that is really obvious, the technology here lies in the first quadrants, which means that the respondent perceive this innovation high potential with a higher risk for being delayed. But for the ODI, they lies in the fourth quadrant, high potential but lower risk for being delayed. Okay, so that's for the general distributions. We see it from the general picture. Now we do a little bit more advanced statistical analysis. We do hierarchical clustering. So basically, hierarchical clustering is grouping or clustering these innovations based on their similarities as much distinct as possible from the rest. And this is what we have. So roughly we can have 5 cluster. So let's see, we have 5 cluster here. So cluster number 1, it has a nuclear fusion, hyperloops, ocean liming, aviation hydrogen, and then DAC. So in general, these innovations who belong to these clusters have low mitigation potential, available post 2050 with high to moderate risk of being delayed. So I want to pay closely to this cluster because I think this is important. The second cluster is iron ore electrolysis, biochar, aviation biofuels, biofuel supply, urban food productions, and producer-customer relationship. So the similarities in this cluster is just in the reduction times between 2030 and 2040. The third clusters, which is also for us is important, is energy storage, battery here, hydrogens in steel making, and alternative building material. So these innovations perceived as high mitigation potential, more likely to be adopted before 2040 with high risk of delay. And then the fourth cluster is all of the CCS technology, and then something, innovation related to food. Okay, so the similarities is the adoption times only 2030 to 2040. Another interesting cluster is cluster 5 because all of the other disruptive innovation, less technological, belong to this cluster. So they have moderate to high mitigations potential, adoptions before 2030, almost no risk for being delayed. So let's pick up several clusters that is important: cluster 1, cluster 3, and cluster 5, sorry. And then we try to do a further analysis to confirm that. We conduct MCDA analysis, which is multi-criteria decision analysis. So instead of finding the similarity, we rank them based on the aggregated answer, and it reflects the priority over the survey. Okay, this is what we have. I don't have a time to explain all, but with MCDA, we could just jot it down. We could elaborate further based on their profession, countries, and gender, but I will not explain all because I don't have a time here, but I'm going to focus on the global solutions here. So according to the expert, technologies, in terms of technology that has a higher ranking or top priority, this include alternative building materials, hydrogen in steel making, next generation storage, which is group 3 here, and uh, iron ore electrolysis. So all of the group 3 belong to these priorities. And then the one that are having a lower priority, this include hydrogen aircraft, hyperloops, uh, direct air capture, ocean liming, and nuclear fusion. So group 1, if you remember in our dendrogram, the clustering, hierarchical clusterings before. Okay, so we got a confirmed result here. Next, if we go to the non-behavioral, uh, non-technological innovations. So the ones that has a top priority, this include all of the mobility innovations, plus the optimizations of thermal and interconnectivity and decentralized energy supply. So group number 5, if you remember before. And then the one that are having a lower priority, this include urban food production, reduce demand for food, and reduce demand for space and material. So it's a bit challenging according to the our expert. All right, so I go to the conclusions. I think that I'm more or less 15 minutes. So what we are doing in this research is evaluating 27 game-changing innovations, non-technological and less technological innovations. Uh, we have a different perceptions about technology, but more uniform perceptions across non-technological innovation. So we have to explore these non-technological innovations because, yeah, the survey said that it is critical in mitigations, so it should be included in our models. And the same thing about hydrogen-based sectors, next generation energy storage. If you still remember, it is in top priority, and decentralized energy supply. Not so much on the NCCS and bio-CCS. Actually, DAC, hyperloops, ocean liming, and nuclear fusions are more likely to be available before 2050, so it's less relevant. So it's not the priority to be included in our modeling decarbonization scenario. I think that's all. Thank you very much.
Thank you, Sujit. Yeah, sorry, I had to change a bit because of like I didn't have good connection. So, is there any question for Sujit? There is. Maybe can I ask all the non-speakers to mute? Perfect. Thank you so much. So we have a question from Connor.
Yeah, I read it too.
So it says really interesting work. And did you look at variation across stakeholder groups or how the background relates to preferences? There was another study that highlights that researchers are over-optimistic about their own field.
Yes, actually, because I do not really have a time to elaborate what we found using the MCDA analysis. So there is actually the variations across the stakeholders. So for example, academics, like the expert who works in academics is a little bit more optimistic rather than the one who works in the public sectors. But mostly the one who works in academics follow the general solutions. So what we have already mentioned is the same perceptions of theirs. We also distinguish between what do you call it, the countries. So it depends on whether it is high income country or low income country. So low income country is a little bit more optimistic. For example, the technology, certain innovations whom we think have a less priority, such as nuclear, the AC ocean liming, the low-income country tend to put that as a little bit higher rank compared to the general solutions. But we do not see any significant differences among gender. But in case that you're interested, we could explore it separately. We could just talk after these conferences.
Perfect. Any other question? Maybe in the meanwhile, I mean, okay, I'm also involved in this study, so there's not, it's not very objective in a sense.
Yes, exactly.
But maybe can you say something more about a bit more about kind of more policy implications of this study? Like,
Yeah, I think that first, like I've already highlighted in the conclusions, that it is now important to include less technological innovations in our modelings. Because as the modelers, that's the obstacles that we sometimes encountered, how we could integrate behavioral changing in terms of in modeling decarbonization scenarios. But by this study, we could direct the behavioral changing through the 4 categories that we have already said, such as in mobility, such as in food consumption and stuff, to be able to incorporate those in our modeling scenarios to reach more realistic decarbonization's trajectory. I could say like that. And then the rules of a certain technology, such as nuclear fusions, that it's getting clear now. So it should be more relevant, should be included in the decarbonization pathway post 2050, not before 2050. Something like that.
Perfect, thanks. If there's no other question, then we can, you can also post them in the chat and we can further discuss them in the end of the session. So now maybe we can move forward to the next presenter.
Okay, I stopped sharing my screen. Thank you.
Yes, thank you, Sujit. So our next presenter is Yeong-Jae Kim, and sorry if I'm not pronouncing the name correctly. He's an affiliated scientist at the European Institute on Economics and the Environment, and his presentation has the topic of international and intertemporal knowledge spillovers in carbon-free and carbon-efficient technologies. So if Young is here to share his screen. Perfect. Yes, we can see that. Thank you so much. The floor is yours. Young, sorry to interrupt. There is no sound. We don't hear you. So maybe there's an issue with your microphone.
Hello.
Yes, I think now we can hear you. Yes.
Hello.
All good. Now we can hear you.
Can you hear me?
Yes.
Okay. Hopefully, my headset does not working. I don't know why, but so let me put it there. Let me reiterate what I said earlier. My name is Youngjae Kim, and this is the co-work by my colleagues Elena Velodili, and happy to present my research. But this is I think some of you have already seen my presentation in many different places already. And this is not a super novel findings, but this is a thing that can be applicable to incorporate endogenous technological learning in IAM communities. So to motivate the research, actually, this is the slide that I really like because it's the frustration as a energy innovation and people who study that area. This is the number of patents over time in climate change mitigation technologies, and after 1990, it skyrocketed, but at some point, like after 2011, it declined rapidly. And lately in 2021, and there's uptick, but still it's not it's really frustrating that we need this type of technologies the most, but is the number of patents, applications, and grantees are not going up rapidly.
Sorry to interrupt, Young. Can you please put it on a full screen so we can see it?
Oh yeah. Sorry. Yeah.
From October last year, I should say. So unfortunately, I wasn't able to update it. The IA hasn't.
And sorry, Stefano Granata, can you please mute?
Hello. Yeah.
Perfect. Thank you. Yes.
Yeah. Can you hear me? Right.
Yes. Yeah, we can hear you.
Good.
Sorry for the interruption.
No. Sorry about really apologize my technical issues here.
No worries.
And this is the slide for the explanation of the technological push and a demand pool policy instrument to stimulate the low carbon technological development. Basically, if you put money in R&D investment in the left part of the graph, and that push the low carbon technological development and the market pools, right? So I think most of you guys have already familiar with these jargons. So this paper, particularly, we focus on the role of the knowledge spillover effect. So knowledge flows, spillovers, basically the positive externality plays an important role in low carbon innovation. Because a low carbon innovation hinges upon both a body of a local observatory capacity knowledge stocks and the knowledge coming from some different places in the world. So international knowledge spillover matters a lot. However, to date, advanced climate mitigation technologies have been developed only a very small handful of advanced developed world. So, but in order to achieve a stringent decarbonization target, new and improved low carbon energy technology with a wide applicability will have to be invented and diffused both in developed world and the developing countries as well. In this context, the knowledge spillover have a big role to play. So one example of a knowledge spillover effect, I just want to take the example of inter-technology sector, a spillover effect. And recent IEA report highlighted the importance of the technological knowledge spillovers, and it can contribute up to 30% of the cumulative emission reductions to 2070 compared to the current trajectory. So if you take a look at the left-hand figures, a offshore wind power plant can be knowledge can be borrowed from many different fields, particularly the aerospace field, carbon fibers, and offshore and gas and extraction and exploration technologies. So to simply summarize the mechanisms, how it works in the spillovers and learnings and everything, I just draw a diagram explaining about let's imagine there is one firm or one country, and then a demand pull policies and like IRA in the United States lately, and the supply push, we put money in the RD&D expenditures, mostly coming from the IEA database, right? So in that case, it stimulates both a learning by doing and learning by researching, and then it develop a firm or country develop new technologies, and that it deploy a solar farms at the end of the day, and it will generate the electricity, and at the end of the day, it reduce greenhouse gas emissions and create jobs, and it increased competitiveness of country at the end of the day. So we copy a additional entity, the firms, and explaining about the international and intertemporal spillover effect as well as the intersectoral spillover effect. So, but in this particular paper, we are not focusing on intersectoral spillover effect. However, we are focusing on the international spillovers between different countries and intertemporal former years and the more recent years intertemporal spillover effect. So objective of this paper is basically to present and update the knowledge about the knowledge spillovers effect in two key set of energy technologies, in carbon-free technologies and carbon-efficient technologies. There are many, many different ways to categorize this type of technologies, but we put in two bins because there are a technology that produce energy without any carbon emissions. Think of just renewable energy resources. And there are other type of technologies that reduce energies and make current technologies more efficient. So that's the type of technology we consider. So there are many, as I said earlier, there are many ways to do it, but still an open-ended question, but we put two bins. So this body of literature that we heavily rely on is basically three key papers, and the most important piece is the Velodilli and 2011's paper. But we use a more recent data, and we use the similar countries, but we expand it a little bit, including developing world, and also we refine a more technological field to incorporate categorize in carbon-free and carbon-efficient technologies. And we have the same proxies for technological and geographical distances and similar proxies for trade area, but slightly updated. And also we have better representation of the environmental policy stringency database from the OECD. And also we heavily rely on two body of literature that speaks about the importance of the knowledge spillover effect. So in terms of the data we use, We use patent data and European Patent Office Worldwide Patent Statistical Data PASTET, and we restrict our attention to the YO2E patent classification, mainly a greenhouse gas emissions reductions in power generation sectors. So there is room for a improvement in our analysis, but this is the future research. So also we restrict our samples in 29 countries between 1990 and 2015. Due to the patent data truncation issues, when we have started the research, this is the most recent data, but I mean, we could add another like 2 or 3 more years in our analysis, but I think the findings are quite similar. So in terms of the patent data, I mean, if you have no idea of the patent data, hopefully I think you are at least know what it is. We measure the number of patent citations between 2 different countries, and the data is coming from the patent data itself, and we keep track of the references. So think of it as there are a bunch of references in your peer-reviewed article. So we keep track of the number of patent citations. So basically, I mean, as you might aware, there are advantages using a patent data, and huge advantages, I would say, and disadvantages of using a patent data set. Literally, I'm not going to go through all those details, but I mean, in most cases, patent data is widely used as data set in this type of analysis. And also, like this is just a reiteration of what I said earlier, and just to demonstrate what different types of the technology that are included in our analysis. And wind and solar thermal, solar PV, and solar thermal and PV hybrid are considered as carbon-free, and technology for improving output and input power generation technologies are carbon efficient. We ignore the 3 and 5 and 6 categories, but in our patent cross spillovers, we included in our analysis, but we only focus on the carbon-free and carbon efficient. So this is the descriptive statistics of what we did, and left-hand figure is the number of patents. Blue one is the carbon-free, and the right one is the number of citations. So both of them are significantly increasing, and in line with the decreasing patterns after 2011 is in line with what I show you guys in the first figure about the general pattern of the declining of the low carbon technological patenting since 2011. So we use a econometric model. So I'm not a modeling person. So we, as an empirical person that apply econometric techniques, we run a bunch of regressions to quantify the left-hand side of this equation. So basically, this equation represents a citing country and cited country. So basically, the citing and citing 2 different type of countries, a fixed effect, and plus the right side of the equation is basically a bunch of several bilateral characteristic of the countries and technological characteristics of the 2 countries, differences and policy differences, and so on. And I will go through more in depth about the one by one. So this equation, the formal equation, represent how difficult knowledge flows from one country to the other. So basically, X1 to X2 to 7 is considered as knowledge barriers between 2 countries. So if the 2 countries are different, definitely there is barriers of knowledge diffusion. The second, if a country located far away, I mean geographical distance, that's definitely barriers, right? The third one is that if they speak the same language, it's much easier. But if they speak the completely different languages, the knowledge flows is not easy. The fourth one is the trade barriers. It's the same context, right? They belong to the same FTA zones. I mean, they are more likely to exchange the knowledge with the person and goods and services and so on. The fifth one is a technological distance between 2 type of countries, right? and which means that either they have similar or same portfolio of technological field. Like the technological field, what I mean by technological field is the technological field that I explained earlier. And the sixth one is basically the level of the technological development of the citing country with respect to cited country, which means that whether a country is leading a certain technological field or laggard of the technological field. The last one is whether two countries have evolved, two countries' environmental policy stringency, or I mean, simply put, a carbon tax is evolved the same way. So this is a simple descriptive statistics, and I'm not going to go over it. And it's more intuitive.
Young? Young, there is an issue, I think, with your microphone, and we can also see you now. We can still see your presentation, though. Maybe if you try to connect again. Okay, we can see you, but we can see the presentation, but we cannot really see you or hear you. Maybe if you log in, log out and log in again, the platform. Okay, let's see. If you can open your microphone, your camera. Okay, it seems that we don't have very good connection with Young. Maybe let's see if this continues for one more minute, and then we can continue with the next speaker. I think also Young was reaching his conclusions in any way. Maybe let's see now if it works. Young, can you hear me? No, it seems there's an issue with the connection. Maybe if Magnus would like to start preparing, and then we can maybe give some time to Young in the end. Okay, this is unfortunate. What can I say? I'm also speaking from the hall, like from the connection that I have. Magnus, if you would like to share the screen, and we can start with your presentation. Yeah. So maybe just a small introduction. So apologies for this technical issue. Magnus Schauf is
We try to have experts from ethics, expert on ethics, expert on psychology, or
Sorry, can you mute?
from economic background. And then we have a panel of engineers, people that are doing technology.
Can you hear me?
People that are managing in public authorities, managing funds.
So can you mute yourself?
We have a mix between academia, public authorities, and also
this is not me, actually.
No, I know, Young. It's someone else that he was okay.
Really apologize my technical issues.
It's okay. I mean, it's already. I think the platform is a bit some issues. Maybe if you can, and sorry for this, Magnus, like for stopping you. Maybe Young, can you shortly sum up, and then we can so shortly conclude, and then we can do some questions at the end if we have time.
Let me conclude. So basically, we draw a knowledge diffusion matrix between two different types of technologies, from early periods and the later period, and the top rows represent carbon freeze, is getting a more significant. However, carbon efficient technology knowledge spillover matrix getting lighter red, which means that knowledge spillover is decreased over time. Conversely, the carbon-free technologies knowledge spillover is getting intensified over time. So basically, this is the punchline. And let me stop, and then we can discuss the other things later. Really, my apologies for the technical issues. I don't know why.
No worries. Thank you also for finalizing even now. And if you have any questions for Young's work, I mean, you can also post it in the chat, and we can also discuss it later towards the end of the session. So now we move to Magnus Schauf. He's a doctoral researcher at the TU Munich, and he's going to talk about system price dynamics for battery storage. So Magnus, the floor is yours.
Okay, I also have some difficulties, but I'll just try again.
Okay, we can hear you though, and we saw before the presentation. So
I couldn't unmute myself. That was the problem.
Okay. So maybe unmute yourself first, and then So now it works. Perfect. Thanks.
All right. Okay. Thank you very much for the introduction. I actually bring a similar approach to Jiong. But the different technology focus, and also a little bit different variables. So let's get into it. So the topic is, sorry again, now I can't. You don't see the slides moving, right?
No, so it's just the first slide.
It's unfortunate.
Maybe if you move it from the bottom left, but there's some buttons there.
Okay.
I think that works.
All right. Okay. Sorry for that. So my talk will be about system price dynamics of distributed battery storage, and just quickly on the background. I mean, probably all of you are familiar with the role of battery storage. Also, the first presentation has kind of highlighted the potential of battery storage to decrease or to improve decarbonization, e.g. by facilitating more wind and solar, or also providing grid services. we also probably know, or all of us know, this great decline in battery technology. So here it's demonstrated for battery packs over the past years, which basically now is 90% cheaper than in 2010. But still, many papers show that actually the end user economics are still quite challenging. And this kind of is our motivation to look deeper into the system price dynamics. So we are not looking at the battery packs, the technology, but in the end, the system price. So the price that is relevant for the investment decision to be made by a consumer or a commercial enterprise. So just a little bit on our contribution. I'll go through this quickly. Just let me know if you want the references. So basically, we use the experience and learning curve literature, and as I said, we focus on total system prices. We use also an extended model where we investigate additional drivers, some of which were already shown to be important in distributed solar PV. And finally, also related to the previous talk, we look at spillover, but not within or across countries, but within the industry between different firms. Our data is from California, and specifically from the Self-Generation Incentive Program, which administers all, or basically the vast majority of storage systems in California, starting in 2008. And until the end of 2021, it has seen about 30,000 systems to be interconnected. And of course, you cannot use all of them. There are some missing values and some general, I mean, you all know how messy data can be, right? But overall, this provides quite interesting and quite interesting data. We have total eligible costs as kind of our price measure, and we have separate various system characteristics and the firms involved, the dates, stuff like this. So very detailed data set with price data that is usually not hardly available for such experience curve studies. Just an overview over the data. So as we can see, basically this market took off in 2017 and 2018 in terms of the number of systems installed. But already earlier, some larger systems. So large in this definition is every battery storage system with more than 10 kilowatts of power rating. So this definition is from the California Public Utilities Commission, and we just follow this. And as we can see, or maybe just also as a notice on your end, as you might know, in 2017, Tesla, for example, started to really roll out their Powerwall, and other companies followed. So also at the same time, California addressed this net metering and started to question whether net metering will be there kind of forever. So as you know, net metering also makes storage less or basically unattractive for homeowners that have a solar system already. And these are some of the reasons that explain this stark increase in the most recent years. However, and this is also in line with what we find or what we see in other technologies, there's huge heterogeneity across counties, and I mean across time is obvious, but also across counties, as we can see in this graph. And this is basically just a part of the motivation why we why we also want to look deeper and not just run a one-factor learning or experience curve. And also, as you can see, this stark increase in demand actually coincided with a stark drop in prices per kilowatt hour. So you can see that on the right. And however, prices since then have not really gone down further. Yeah. So our model, we start with a very simple log one-factor learning or experience curve model. I will use the term experience rate now because we have price data and some literature uses it in this way. However, there's actually, I mean, the literature not really consistent on using or differentiating these terms. So yeah, as I said, it's the basic one-factor model. So we have the cost, or in our case, price measure on the left as the dependent variable, and on the right we have experience, which we measure with the cumulative number of projects as our main, and in this case only, explanatory variable. And then beta 1 is the learning elasticity, which is most interesting for quantifying the relationship, but also for using it later on in system models, for example. And usually this elasticity is then transformed into the so-called learning or experience rate as 1 minus 2 times the beta 1. We extend this model to account for more effects, not just experience. And later you'll also find out why we do this. First, what we add is the HHI, which is a measure for competition. We also add some economies of scale, or control for economies of scale, which we measure by the system size in kilowatt hours and the duration. So the ratio of storage capacity to power, and some fixed effects, as we've seen. There's just huge amount of heterogeneity. So we at least control for the time invariant part of this heterogeneity by adding fixed effects. Maybe kind of surprising, given the huge learning and experience rate in the battery storage technology. We rarely, or we almost find no or very small learning rates or experience rates, let's put it this way. So they are between 1 to 3% depending on the measure. And also importantly, the fit is really poor. Yeah, I mean, it's clear that the fit is not as good as in a time series setting, because we just have single projects, single observations. So of course there's some heterogeneity, and one variable won't be as good as in explaining this as in a setting where you just have to fit a curve through 20 or 15 years. But still, it's very low. So that's the first argument for us to really go into it a little bit more in detail. And what we do is first check, okay, we have these large systems and these small systems, maybe there's a difference. And actually we find that yes, there is. So these larger systems, remember, these were systems with more than 10 kilowatts of capacity, they show experience rates of 11%. Yeah, remember we had 1.3 as the average for across all systems. So these large systems, which are less in terms of the number of systems, they have a much higher experience, much stronger learning. And also the fit seems visually relatively okay. On the other hand, we can see that for the small systems, we find some negative learning, and not really a huge, a good fit. So in columns 1 and 3, you find the corresponding numbers to these graphs, and basically when you look at the adjusted R squared, this confirms what I just told you. The fit is much better now for the large systems and still very poor for the small systems. So how will this change with our extended model? And what are the findings of this extended model? So the findings are first that learning rates or experience rates remain relatively similar even in this extended model. But we have basically now 3 more important predictors of prices of distributed storage. And I'll just focus on small systems because there we so far were not really satisfied with our main predictor experience, right? So what we find is that market structure actually matters a lot. So I mean, HHI is the only term that is not logarithmized. So the coefficient, you cannot really compare the coefficient directly to the others, but still it's a significant effect of HHI on the prices. So what does this mean? Less competition is associated with higher prices, and this is basically what we find. So next, the economies of scale are also highly significant, and here it's also the expected relationship, namely that larger systems in terms of storage capacity, even within these segments, and a higher duration, so a larger capacity to storage ratio, are associated with lower prices. So it seems like these soft costs or balance of system cost components, like competition, for example, are somewhat behind this effect. So yeah, and they are. So we can see here that the experience rates, especially for small systems, change dramatically when we just look at balance of system costs. So we define this as total system prices minus the battery hardware prices. We don't observe them in the data, but we just match the annual data from the Bloomberg New Energy Finance, from the Bloomberg Battery Price Survey. And yeah, basically this confirms, or this just illustrates that the components other than batteries, so this soft cost components that are especially relevant for small systems, are driving these low learning effects. And basically this resembles the kind of soft cost challenge of distributed PV. And this obviously then leads to the fact that the share of non-battery costs in this total system price increases over time, and it's now about 85%. So 85% is permitting, markups of installers, labor, other installation-related material, but not the actual technology, yeah, which you might think offers some opportunity for reducing these costs. Our last analysis looks at spillover effects, and again we just want to see a little bit, okay, do we find further support for this problematic learning, or basically this absence of learning in non-battery prices? And actually we do. So we separate our experience measure in this case into 2 components. First, we have the industry experience, which is here the variable spill, and then we have for each installer firm separately the experience by the installer firm. So at a time t for a given installation, industry experience will capture all the total number of projects minus the projects of the firms that is installing this specific project. And what we see is well, there are spillover effects in a way that the total industry experience has a negative effect on prices, but firms that have more experience charge higher prices. So apparently consumers are willing to or have to pay for experience, which obviously is again a soft cost component and basically implies markups for more experienced firms. We run separate. I mean, you can also see here our other results in terms of HHI and economies of scale remain also in this model, and also all of our conclusions are similar or basically virtually unchanged if we work a little bit on assumptions. For instance, the definition of experience, but also the fourth one is quite important, as SolarCity and Tesla observations might be actually appraised value, so it might actually have appraised price values. Maybe you recognize some clustered data in the graphs. This is mostly due to SolarCity and Tesla, but results remain generally similar. So overall, we can say that the total system price learning strongly falls behind battery hardware learning, but it comes closer when we look at large systems. Yeah, and this is probably due to a lower importance of competition and other soft cost components for these large systems. And finally, also important, more experienced installers charge higher prices. So our key takeaway is we should foster competition and we should continue to scale up markets, but also systems to make battery storage more affordable and thereby facilitate higher adoption. So I'll just sorry. So let me just rephrase or reorder this. So policies, for instance, to speed up this learning or to harness the economies of scale are increasing transparency. For example, crowd platforms which begin to emerge in the US, for instance, and also standardizing regulatory processes, bureaucratic processes, and finally, probably most interesting for the topic of this conference is that we see actually a value in granular modeling of technologies, as we saw, for instance, this large difference in experience rates in our sample, which can also, or in general, our results can also be used to see a difference between global and local learning, right? So global learning, this strong learning in battery technology, and local learning, basically very poor or absent learning in total battery system prices. Thank you very much.
Thank you, Magnus. Great work. Thank you for this presentation. Unfortunately, because we're going a bit late, we will not have time for questions. There's already one in the chat. So if you can, maybe write your answer there and respond also to other questions there. And I would ask Lydia to prepare her presentation. Sorry for this, because of these technical delays, we got a bit, unfortunately, not much time for Q&A, at least in a speaking way. So the next presentation is coming from Lydia Stermieri. She's a PhD student at the Paul Scherrer Institute in Switzerland. And her presentation is about a socioeconomic energy model to include societal changes influenced by digitalization in Swiss net zero energy scenarios.
Yes. So thanks a lot for the introduction.
Hello, Lydia.
And I'll try to share.
Magnus, if it's possible, mute your microphone. Thank you. Thank you so much.
No?
Lydia, we can see your screen.
Yeah, but that was not my screen, so I'll try again.
Oh.
I don't know what was. Oh, no.
Okay. That's very Kersian.
That's magic.
Can you see now my screen?
Yes, we can see it. If you can put it on full screen,
yes,
that would be great. Change it. Yeah, sure.
Now it's good, right? Perfect.
No, wait. We still cannot see it. Maybe can you do it again? Like, and so try to share it again.
Now?
No, can't really see it.
Good. No. Let's try again.
You can try to reshare it and then change the PowerPoint.
Yes. This one?
Yes, and then if you put on full screen, but then press or like from view.
Now?
It's still not saying.
Okay.
Yeah, so maybe you can do it like this. I mean, if it's something very small, maybe we can still zoom in a bit.
It's still not working.
No. But still, it's fine. I mean, I think we can read it.
Maybe. No, I really cannot do anything.
Yeah.
Okay. I'm trying my best, but I don't see what is the problem. Why you cannot see it? Okay.
Well, it's fine. If you can move now between slides, then keep it as.
Yes, I hope you see something and.
Yeah. I mean, we can see it. It's just.
Okay, perfect. So at least we can continue. So, okay, thanks a lot for the introduction. As I say, I work at PSI at Posher Institute as a PhD student in the Energy Economics group. And today I will just introduce you to the framework that we create in order to have a socio-economic model to analyze energy transition pathways. So yes, I will. This is the agenda, and I will skip it, and I will start with the motivation. So of course, as we know, we want to achieve the net zero emission in 2050, and we, let's say, all agree that a future zero carbon energy system entails social and technical challenges. So the aim is to try to find a technical and socioeconomic feasible pathways. So what does it mean? So a technical feasible pathways means are estimated with the uncertainty in the development of some future technology for the energy system, while a socioeconomic pathways include also the social systems and consider the acceptance and the well-being of the population. So our aim is to connect these two pathways together. And as an additional point, since we want to analyze what is a socioeconomic feasible pathways, we also recognize that in the new era that we are living, digitalization will play a big role. Especially because now it's giving the consumers the opportunity to select their own technology, both for the supply and the demand of energy. So the last question is to try to also integrate digitalization and understand what role it will play for the energy transition. So how we did this? Yes. The methodology that we develop is based on two different models. So with the first model, we want to analyze technology diffusion, social acceptance, and the behaviors of citizens and their preferences. And first, we decide to adopt a social practice theory to quantify this energy consumption, the implication for the energy consumption. To shorten, what is the social practice theories? Basically, the social practice theory says that each person or individual needs to perform some social practices, or if you want to say also has some lifestyle or normal activities, and in order to perform these activities, it needs to consume energy. So if we analyze how the practice change, we can also have an idea of how the energy demand will change. And especially if we think about digitalization, we know that the introduction of information and communication technology has transformed some practices, enabling new ones. So one of the common examples is thinking about the possibility now to work in remote compared to going to your own place. This change in the practice of working also changed the demand, the energy demand connected to go to work, eat the offices, etc. The second important point is the social practice theories relies on information flow. So you need to have communication networks in order to understand how the information spreads into the society. And this is good if you want to analyze what is the social acceptance and how preferences spread into the population. And so this is the theory that we decide to apply, and the model, the approach that we apply is the agent-based modeling approach. You can see a small representation of how the agent-based model work. And the main concept are that there are several actors, and the main one are households and companies. And here we are talking about like 500 agents that will be representative of the countries that you are analyzing. And the idea is that households perform some social practices. In order to do that, they need to use some technology, and then they, through the interaction in social network, they also exchange their behavioral preferences for practices and technology. At the same time, some of these practices can influence or enable digital business models, and so there is also a change into the companies. And for companies, we mainly refer to the tertiary sectors, where in the last year we have seen that that this became one of the most relevant sectors, and that is mainly connected with households' lifestyles and decision. Few information, there are at least 3 sectors represented in the agent-based model, that are the transport, residential, and the service. Is cover a long time period. On an annual basis, it goes to 2050, and is dynamic over time, which means that both the transport, the residential, all the technology involved, they evolve over time. So they have different invest price. They have different efficiency, there are different energy prices, and so on and so forth. And also, of course, the population evolve over time. Here you can see what are the decision process that we consider for households and for companies. And one of the main things is that we maximize utility of households, and we consider three main components. One is preferences, the second is cost, and then infrastructure, which means that in our model we not only consider the best technology from an investment point of view for the households, but the utility also considers some preferences like environmental awareness of the households, so which technology best fits your preferences from an environmental point of view, for example. And it also then there is the third component, infrastructure, consider if the technology that you want to adopt is available or not. So, for example, if we think about electric cars, this infrastructure component also simulates some anxiety by the fact that you don't have the infrastructure that you will need in order to drive your car as you would like to. So all these information are included. The second part, sorry, I don't know, okay. The second part is to analyze the impact of digitalization for the whole energy system. And in order to do this, then we couple the agent-based model with an energy system models that is developed in times. Here on the right, you can see how the connection and the coupling between the two models works. And since, as I will tell you later, we apply this model to Switzerland, here you have a representation on the Swiss times energy system model that is called STEM. But mainly how it works, the coupling between the two models, there is a soft link coupling with 80 connection points between the two models. And for example, as you can see, the Swiss times models gives the technology cost, the efficiency, the energy prices to the ABM. And then the agent-based model gives the diffusion of technologies, the preference, and some infrastructure development that also became the input of the energy system. And there is an iteration between the model until convergence, with the convergence criteria applied to the energy demands and also the share of the rate of the technologies, the share of the technology adoption. And basically, thanks to this connection, we are able to inform the STEM model usually has a central agents approach to what are the social preferences. And in this way, we don't have only a cost optimal solution, but we have a solution that is feasible both from a technical point of view, but also an economic point of view. So as I say, we then to show you how it works, an application, we apply this to Switzerland for two main reasons. The first one is that it already exists a net zero scenarios for Switzerland that has been developed in the joint activity scenarios and modeling. And as you can see here, we already, let's say, know how we could reach the net zero scenarios. And the other reason is that actually Switzerland has a digital strategy where they consider how you can implement some digital business models, how can you implement the digital empowerment of the population, etc. And I have to say also the fact that the 75% of the Swiss GDP is generated by the service sector also help to analyze Switzerland with our framework, where we analyze basically we also have as agent the companies that represent the service sector. So the idea is that we have these two components, but they are not integrated. So basically, this is what we want to know: what's the impact of including the also digital concept in the net zero scenarios. And now I will show you some. We may mainly have two scenarios. Now I will also show you some preliminary results of a third scenario. But in short, in the worst scenarios, we assume that the adoption of several digital practices and ICT used by the population will follow the observed trend of 2020 over the entire time horizon. While in the E world, we assume that this digital practice and ICT and everything will grow by 5% on average in the time horizon that we are analyzing. And then I will show you a few results about the eco world scenarios that has the same assumption than E-world scenarios, but plus we assume some information campaigns and education to drive the preference of households towards eco-friendly technology. The other things is that of course, all these scenarios have as a climate target of 0 megaton of CO2 in 2050, and there is a CO2 tax that increase over the milestone years through the horizon. To show you how the framework works, we made a simple application that was the telework, and we consider how the teleworking practice in Switzerland will evolve. And we want to see if the evolution of this practice can already have some implication for the energy system. There are some assumptions related to these scenarios, for example, working from home will change the demand profile, and it will have an impact of the heat demand and the electricity demand. And this is true both for buildings, residential buildings, but also offices, for example. And then there will also be a reduction in commuting demand, and these are only a few of the assumptions that I will show you, just to understand a bit better the results. So what we can see now, if we compare these two scenarios for this specific digital practice, well, in the upper part of the graph, maybe you don't see it so well because it's not in there. Okay, I hope you will see it. Basically, here we see how it changed in the two scenarios, the adoption of this practice by the population, and in the bottom part of the graph, we can see what is the impact on the energy demand. So, as we said, we imagine there is a reduction in the BVKM of passenger transport demand, while there is an increase in the residential energy demand, both from heat demand and electricity demand. And there is a general reduction in the petajoule of the service sector energy demand. And I have to say that in this energy demand, we also include that more digitalization will increase the electricity demand for network and infrastructure. So we assume that this will increase, but we will also have some decrease thanks to digital business models like working from home, also for the office space. So what are the implications of this change in the energy demand for the energy system? So as I said, we pass all this information to the energy system model. We inform the energy system model, and after the iteration, these are the results. In the A graph, we can see the CO2 emission in 2050 as a result from the energy system model. And we can see that the gray one is the digital world, while the blue one is, let's say, the business as usual world. And we can see that the main difference is between the transport and the residential sector. So the digital worlds actually increase the CO2 emission in the transport sector compared to the analogic world. And why is that? So basically what is happening is that the reduction in the transport demand due to the reduction in commuting decelerate the renewal of the vehicle stock and the penetration of renewable technology in mobility. So basically the fact that you use less your car also hinder the introduction of electric vehicles because you are less affected by CO2 tax or in general by the increase in the energy prices. How the system reacts in order to offset this increased emission from transport, it needs to increase the share of renewable technology and heat pumps, for example, in the residential sector. At the same time, we can also see that since now the residential, some biogenic fuels needs to be switched to the residential sector, then industry will also be affected, and this will imply that the energy convention sector needs to deploy more CCS or more direct air carbon technology in order to still meet the net zero scenarios. So this is one result that even though, as we can see, even though the demand doesn't change too much, the connection between these two models already show up that there can be a different energy system configuration. And the second results that, as I say, are only preliminary results is this eco world scenario, where basically you want to see, okay, if we implement some information campaign where we can increase the environmental awareness of the population, what will happen? And we have seen that thanks to information campaigns, if the environmental awareness increased, then well, we can have an increase in the demand for the electric vehicles compared to the analogic world. And so in this case, we are able also to see the reduction in the emission also in the transport sector. And by this, we can also see that the overall cost for the energy system in the eco world is lower than in the analogic worlds, thanks to the fact that now in this configuration we need less investment in negative emission technologies, for example. And so to conclude, the key message are that the introduction of the social expert into the energy system models provide different configurations of the energy system that also results in different investment in order to achieve energy goals. This means that there is also different energy supplies and dependencies on the surrounding countries that needs to be considered. And in the end, we are analyzing basically how policies that able to influence energy-related behavior and environmental awareness can help in inducing this behavioral change that will accelerate the energy transition. So I conclude. I thank you all for the attention, and here are my information, and of course also the information of the Switcher that is which finance and my PhD. And if you are interested in see what we are doing, you can visit the webpage. So thanks, and I hope I was on time.
Perfect. Thank you, Lydia. We're exactly on time, and yeah, very interesting work as well, and very good presentation. We're looking forward for more results for your following work. Well, I think I'm unsure if the platform will finish. Will just shut down. So theoretically, we still have some minutes, maybe for some questions. If you have some time, or if there is any question to Lydia, but also to the other speakers as well. The first question from to Lydia from my side, like how you quantify preferences? Like what kind of data do you use, to make the measure?
Yes, thanks. That's exactly, let's say, one of the tricky points, but also why we think that this model can be interesting. And basically, the preferences now, we create a synthetic population, first of all, that is representative of the country. And then the preferences are initialized with the Shell survey, that is the surveys for the Swiss households in Switzerland. And so basically each preference for each specific technology is initialized thanks to this survey, or let's say we try to extract the most data as possible from the survey.
Perfect, thank you.
Thanks.
If there is any other question to Lydia and the other speakers?
I would have a question to
Yes, go ahead.
Georg. I was wondering whether you can somehow, with your model, address also, let's say, globalization, because you have, if I understand correctly, you have country-specific patent data, and basically you probably generate like a stock of patents by country, right? And I mean, I totally understand what you're doing and why you're doing this, but I was a little bit, or I'm wondering how you can account for example, multinational companies that are in different regions of the world. Yeah, so.
Thank you for your question. In terms of a firm level of or industry or sector level analysis, yeah, you are absolutely right. But in terms of the cross-country analysis, patent citations, we count the number of patent citations basically, not the stock of patents per country. So it doesn't matter, but like you pointed out, the importance of the multinational firms, firm level analysis or firm level of global learnings and local learnings, I mean, it's tricky part. It's really tricky because a one firm could belong to the brand and headquarters of the different countries and so on. So it's really careful approach to disentangle allocate the patents to different part of the companies. That's a really time consuming, and I think maybe someone tried in the innovation literature per se, but I haven't come across in this domain, particularly energy, low carbon technological field domain yet. Maybe I could be wrong, and maybe some literature already.
No, okay. Yeah. So then my follow-up question would be: do you know the share of? I mean, who is behind these patents? Is it mostly universities and individuals? Because then, or let's say national companies, because then obviously your measure is very good. But if it's mostly these multinational companies, then the question is, okay, how can you maybe improve it? Because if, let's say, for Denmark, all the wind patents come from Vestas, then maybe it's a different story, right?
Yeah. I couldn't agree with you more about it. And frankly, we do have the data of types of the patent applicants and the inventors, I think, but we haven't really carefully looked into that type of the entities. So I don't have answer for your question now, but I think it's really interesting point to dig into further. Yeah, thank you.
Yeah, thank you.
Yeah, thank you. Yeah.
Perfect. If does anyone have another question for the speakers? There are also, if you have another question but you don't have time to post it now, there is also, like, you can post it through the platform of ECMP. You can contact its speaker by clicking on its name, and then there's a text box that opens, and then they can receive also your question.
I might have another question to Sigit,
please go
the
ahead.
first presenter. I was how was the technology selection done? Because, for example, what I read about a little bit in the last weeks, what some people are saying that we should already invest in now is this everything related to this basically geoengineering topic in terms of solar radiation management or other stuff which I'm not an expert of, but just throwing in these buzzwords. And I think you didn't include this, so I mean I was just wondering what you would expect for such or for these technologies, where you would maybe also add them in your graphs.
Okay. Sorry. So yeah, basically the selection is based on the study of NAP. I've already told you about, like, the ones that we pick to be evaluated right there. So I didn't really explain it in details, but in the paper, she classified the technology based on the technological readiness level. So between 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means that the technology that has been widely and commercially available, I think from 7 to 9, we exclude that, and we focus on the list of the technology that is still under the certain stage of the research, or like a small scales of development, which is 1, 3, and 4 to 6. So that's the list of technologies that we have that on the survey. Of course, it's not really, how I could say, satisfied all part, because there's still another, probably what do you call it, another technology that we missed, right? So in our paper, in our survey, we also asked about the certain technologies that we missed to include, to be evaluated, and they say something, but it's quite different from one region to the other region. So that's how the MCDA analysis is quite interesting. So we conduct that things because we could basically knows about the tendency of a particular country toward a certain technology, whether they trust that technology or not as the media for deep decarbonizations, or they tend to be quite skeptical like that. I cannot give like an exact answers about that geospatial engineering technology, but how I could say that is the general depictions about how different expert from different professions, different country might perceive a certain innovations in a different way. I hope it's answered your question.
Yeah. So was maybe you know it, in these free fields, kind of open fields, what was the most mentioned technology that you missed?
I have to take a look at this. I think that I have this one. Let me check first. I didn't include that because I think that I didn't have a times, but happy to check this one. So let me check. Sorry, I hope that we still have a time for this. So, oh yeah, so okay, so for technology is, they mentions about photocatalysis, and then the digital technologies, something like that. But I think that we have already mentioned this, not in terms of technology, but much more on other disruptive behavior, innovation, sorry. And then they also mentions about the deep geothermals, but like we didn't really include geothermal because in some countries they have already depends on geothermals for the mitigations, but they still mention this. They mention a lot in terms of non-technological, such as sustainable farming, and then clothing material changing, circular economy, something like that. But I think that if we take a look at on the definitions of each of the innovation, it is like intersecting each other. So probably we directly have already mentioned it in as a part of our survey, but it's not really that clear that we go into that direction, something like that.
Maybe to just shortly add, we had also some general engineering technologies explicitly, like ocean lime, for example.
Yes,
you
true.
could think of it
Correct.
in essence.
Yes.
So,
yeah.
and we couldn't have, like, say, the whole range of them because we tried to have a wide range of innovations from different, say, sectors and types. So,
yes,
yeah.
correct.
Thank you very much. Very good answer.
Think so. Well, if there's no other question, I think we can leave it here. Yeah, thank you to all the speakers and the audience for being here. And I apologize, for the technical issues that we had. I hope that we had. I mean, it was, at least for me, it was very interesting, like, to see all these presentations. And if you have any further questions, please don't hesitate to contact the speakers. Yeah, thank you for everything, and have a nice.
Last thing. Now is a coffee break time, but at 4 the poster session will start. So on Spatial Chat, and you can access from the B2 Match platform, so the conference platform. So see you later at the poster session. Bye.
Perfect. Thank you. Bye.
Bye.